Let's hope. Could you? Great. Okay. So, I realize I'm all that stands between you and lunch, but I will try to be concise but not speak too rapidly. As you all know, we've made amazing progress in cosmology in the past century. When I began in the field, we were discussing facts of 2 uncertainty in omega and dark matter, all sorts of things. And now we're dealing with 1% level precision or better. But there are 2 big questions that are still remaining, maybe more, but these are the 2 I'm going to focus on. What is the matter and where do we come from? Okay, and this is the summary of my talk. I'm going to say a little bit, really a review of dark matter, and give you 1 or 2 sort of exciting developments in the field. I'll talk about primordial black holes, and then I'll talk about primordial non-gaussianity and ways to go for that in the future. Okay, so what is the matter? Okay, we have a lot of dark matter. It's been very frustrating, but we've had a beautiful theory, or framework for a theory, perhaps, which is thermal freeze-out from particles produced early on at high energy, WIMPs, weakly antimatter particles, and the beauty of this is that they freeze out roughly, they stop being created when the temperature is roughly 1/10 of the rest mass, and then you just have a residual level frozen out depending on the cross-section for annihilation, and if that cross-section is too large, there are too few. If it's too small, there are too many. And so it's a bit like, the Goldilocks problem. We suddenly can get the right value of omega in dark matter, and this is the expected value of the cross-section for particles that we know nothing else about. So this is an amazing guide, of course, for the theorists. And so here are the ways we look for these particles. The idea is that they can scatter off known particles in deep underground detectors, placed there to avoid cosmic rays, and you can look for recoil effects on the target protons. You can look at their Majorana particles. They self-annihilate, as they did when they were produced in the early universe, and so in the depths of the dark halo, even though the time scale is incredibly long, there are enough of them for you to get interesting things, high energy gamma rays, neutrinos, or whatever. And then finally, you can even produce them in general and accelerate like the LHC in principle by looking for missing energy or missing momentum events. Okay, so it's been very, very frustrating. The bottom line is nothing has been found, of course. This is a summary of direct detection as it is now. There's this one report from Dama using Soviet iodide crystals based on modulation by the Earth's orbit around the Sun, with a detection, many sigma claimed, but many, many experiments have pushed below that, and we now, this is the cross-section versus with mass parameter space, and future experiments are going to take us even lower. We're on the verge of getting to the ultimate limit, which is due to neutrino interactions between the atmosphere and the Sun with your detectors. And so that will require us scaling up from the current generation of tonish detectors up to maybe 100 or kiloton detectors, and that probably will be as far as we can go. You run both out of parameter space to search for, but more especially money, because these are getting to be very, very expensive. And it's incredible how so many experiments around the world are participating in this search. The deepest one is in China, of course, producing results. So that is the story on direct detection for WIMPs. So far, interesting upper limits. Let's talk about indirect detection. So this is very exciting because I get high-energy gamma rays in particular, which are, there are beautiful experiments looking for these, such as the Fermi satellite and the CTA, which is the future, but this is the Hess-Cherenkov radiation telescopes looking for showers produced by events produced by very high gamma rays in the Earth's atmosphere. Okay, muon poor shower, basically. Okay, so experiment, Fermi in particular, studies the galactic center. There is a residual excess seen in the central few degrees. And this is when you take out all the other templates from molecular gas and known sources, etc. And this is exciting because not only does this more or less agree in profile with density squared for the presumed dark matter, which is what the annihilation signal should be. It also is more or less spherical, like the inner halo probably should be. It more or less gives you the thermal type cross-section that we're looking for. And finally, you can look at the spectrum, and it fits beautifully with predictions from some particular, lightish 10 GeV particle self-annihilating. So that looked very good for a while. It's the strongest hint we had, I would say, but recently it's become clear it simply doesn't work very well. So a deeper study of this area showed there were enough weak sources and lots of fluctuations in the gamma rays, and the most recent result from the Fermi satellite again shows that if I now add up all the known sources, all the millisecond pulsars in the inner region, and then if I include my possible dark matter contribution, I simply fall short of the observational data. I have to add a contribution of point sources which account for the excess fluctuations, and then I can run into this region. So it doesn't look as though that strong hint, I would say, doesn't look very good for a dark matter signal. The other place you want to look for dark matter is in regions where there is lots of dark matter but no interfering millisecond pulsars, right? And so, or perhaps very few of them. And so those are the dwarf galaxies. We know they have huge amounts of dark matter from measurements of the stars. You can barely see the stars in these pictures, very few stars to get in the way of your dark matter searches. Again, studied intensively by these experiments and others, not a hint, apart from one possible 2 sigma detection, of anything that might possibly be dark matter. Okay, so it's very frustrating, and the question is, we have to ask now, what if we simply don't find dark matter in the next decade or so from these types of searches? What do we do next? Well, many of my ingenious colleagues say, let's modify gravity. Let's show Einstein didn't quite get it right. There's something there that's mimicking dark matter. And this is a great industry at the moment. But when you go to the relativistic consistent Lorentz invariant types of theories, you have a huge variety of possibilities based on many of them being metric theories, not all, but they're all incredibly ugly compared to Einstein, and what is more, they're all basically designed to address the dark energy problem rather than the dark matter problem. And there are very few of these. In fact, I don't think there's a single one that really is a plausible dark matter and dark energy combined explanation. That might be the way to go, but there is another possibility, and that is, we are looking under the lamppost for dark matter. This is the parameter space that's out there. Huge range in cross-section of mass. We've only studied, look at the numbers of decades, right? From incredibly massive objects, these would be primordial black holes, or very, very light things, axions, ultralight axions, string theory motivated. And we just studied this tiny part of parameter space with a limited amount of theories. So we have a long way to go. And let's see, okay, so what I'm going then to, so when you start moving away from this WIMP area, you get into more exotic types of particles in many cases. I'm going to talk to you about 2 examples, self-interacting dark matter, fuzzy dark matter, and primordial black holes, as some of the more exciting things that we're thinking about at the moment. So why? It's not just the search for dark matter that's motivating. There has to be something else as well that tries to limit this huge parameter space. And so what has got many people on the particle side excited is the so-called dwarf galaxy problems. So this is the number density of observed dwarf galaxies, and this is the current state of the art. When you take the cold dark matter prediction, this is going down to lower and lower mass. This is the number per unit volume per unit mass. So the simple theory predicts an enormous increase when you try to put in things like feedback from basically exploding stars, supernovae, to kick out some of the baryons when the first stars form and stop later stars forming, which you can do more easily in dwarf galaxies than big galaxies because they have shallower potential wells. So all attempts to do that have a very hard time in getting down to the data. And that's basically because this is a very complicated process. So that's one problem, the number density. And the other one, which is connected, is that all of these dwarfs seem to have cores in the dark matter. That's to say, there's a simple prediction from the simulations for a power law density spike in the center, the so-called NFW profile of 1 over R divergence. But what you find, in fact, is a core, and you measure that in the rotation curves. So this is the data on a number of nearby galaxies, and in this brown is the basic cold dark matter. So the black is the cold dark matter prediction, well away from the data, and the brown is the warm dark matter prediction. Now, naively, I think warm dark matter, that's great. That gives me free streaming, and that suppresses the dwarfs. But at the same time, it doesn't explain the cores properly. It's one thing getting rid of the numbers, so it just simply doesn't work well. So, of course, you can add more degrees of freedom. You can add other types of feedback. But the one particle physics model that does work, and there is one, okay, which is interesting, is so-called self-interacting dark matter. And so this is dark matter that has a huge cross-section, basically on the order of 10 grams, 10 centimeters squared per gram, 10 times the Compton value. And it's designed to work only on dwarfs. If it were this high in galaxy clusters, you'd kill those. So you put in a strong velocity dependence, dispersion, in the cross-section, and then lo and behold, it seems to, the blue line, so you can go through the data nicely. So that's one example, an exotic type of dark matter that can at least explain dwarf galaxy data that's been worked out in some detail. Okay, here's another exciting option, which has not been worked out in very much detail at all, but this is exciting from the quantum mechanics point of view. Because if you have, again, string-motivated ultralight axions, it turns out that, basically you have a macroscopic quantum scale if you make the particle light enough. The de Broglie wavelength is kiloparsecs, okay, in dwarf galaxies. Exactly the scale you need to start, because this is basically the dark matter becomes fuzzy at that point, below the de Broglie wavelength, to generate a core. And so that's all very exciting. There's an exact solution for the nonlinear evolution of this from the Schrödinger-Poisson equation. And it turns out that in the center you have a Bose-Einstein condensate, actually like a soliton, and then outside these ultra-axions look just like cold dark matter. And so there are constraints on this. You can look for kiloparsec scale features in the Lyman alpha forest, that's absorption lines to distant quasars. In hydrogen, controversial because they're very hard to model, but here's a really exciting prediction for the near future because of this soliton, and it's a purely quantum effect on macroscopic scales. It's amazing. So this soliton has a Compton frequency, right, from the oscillations, and that will give you a millisecond pulsar timing signal, and that's sort of one of the predictions that is exciting for that class of theories. And the details of whether it can explain the dwarf anomalies have not been worked out thoroughly, but I think it's got great potential. Okay, so the final example I want to show you is primordial black holes. Now, why primordial black holes? Well, here are the known black holes, right? So far, we study black holes in the stellar mass range, up to 30 or so, 60 solar masses post-LIGO. And in the supermassive range, where we're seeing lots, which are inferred, our galaxy's got a 4 million solar mass black hole. The nearest big galaxy has a 6 billion solar mass black hole, the M87. And so could there be something interesting in between? Maybe so, and they could be astrophysical black holes, made in much the same way as these big ones are, more of the same, or possibly primordial black holes, okay? Why are primordial black holes of interest? Well, this is why, basically. You saw the LIGO detection. Here it is. Prior to LIGO, these are the black hole masses that were known. LIGO suddenly gave us these three masses outside the range of what was expected or predicted, okay? Therefore, of course, people rapidly adapted their modeling of astrophysical black holes. These are now can be made easily enough, but it does suggest there might be another pathway, okay? And so this triggered a number of papers saying, aha, maybe these are mergers of primordial black holes. Okay, and if so, that's a nice prediction to expect a whole range of masses, because with the astrophysical ones, you are limited by astrophysics. You can't make them too big from normal stars because they go pair unstable, and so, you know, they're a beautiful test for the future. But that's another story. Let me just show you now the limits we have on primordial black holes, okay, from recent papers. So this is the mass range of primordial black holes, from, in this case, from a tenth to 10,000, and you have limits from microlensing, limits from the Planck satellite, because accretion would realize the universe. So you can see, notice this is 1/10 of the dark matter. Okay, so there's a tiny window if you want it to be the dark matter, basically, which might work around 30 solar masses. That's you know, one sequence of papers that pushes that. But you know, if you take the more general view, it might be spread over a wider mass range. You see, you have a fair amount of freedom here, and if you worry about even a small contribution, even 10,000 solar masses is pretty good. Well, that's not the only study. There are others, and so this is another one. This is Garcia-Bolido's preferred suggested mass range for primordial black holes. Again, the total adds up to the dark matter, more or less, and it covers the range from in solar masses all the way up to 10,000 solar masses down to Earth-type sizes. You'll get from all ranges. Another one, if you ask what is the best window on the smaller scale, this is all that's left now. Okay, 10 to the 20 grams if you want to have low-mass primordial black holes, and if Francesca doesn't let them evaporate with quantum gravity, then these are great candidates for dark matter, 10 to the 20 grams. But that is the one thing. This is the latest hyper-supreme limits on microlensing, etc. So it's really being squeezed to a very tiny mass range for the sub-solar mass primordial black holes. That's another possibility. And then the future is great, because again, it turns out that again, millisecond pulsars will be great ways of probing dark matter too, and it is thought that their timing, Shapiro timing delays, will basically be able to set very strong limits in the 1% level in the near future. So that's the future. Okay, how do you make them? Okay, so this is one of the interesting questions, okay, which is a little bit, which is interesting because it ties in with all we've heard so far in this meeting about the very beginning of the universe and the nature of the primordial fluctuations. Okay, so the idea in one, I think what is maybe the simplest way to look at this is that you have isocurvature modes which are scale dependent. Okay, so on large scales, Planck has ruled them out completely, but let's go down to very small scales where who knows what is going on, and you can imagine putting in some feature into your primordial conditions, and provided you get up in the density flow, this is the power spectrum, up to of order, you know, so this is 1/10 the density amplitude here, then rare fluctuations will make black holes. They'll be large enough on the horizon scales, the first end of the horizon, to give you black holes. Okay, so that's beautiful, and you know, it's exponentially sensitive. Okay, I raise this a little bit, I get vast numbers more of black holes. Okay, and they don't affect anything on the Planck scales. And if there are intermediate scales of black holes, there's a really interesting prediction. Okay, and that is this. Here is the modulation from larger scales, and again, if I take out that larger scale modulation, suddenly I get clustering. It's like, you know, mountain peaks coming together. This is where the primordial black holes might be clustered. Okay, they're biased basically. So that's another logical thing that's going to happen, and that has not yet been worked out in great detail, but that's fascinating. Okay, so what is interesting? So I think that for this case of black holes, primordial black holes, there's a real window in astrophysics to fill, which is roughly at the 10 to the -4 in terms of omega dark matter. So it's small, but it should go along with anybody's model for primordial black holes. It's a small part of them, okay? And why is this so interesting? And the idea is that we are beginning to see now in observations evidence for black holes, massive black holes in small galaxies. And because these are in between the small ones from the stars, the big ones in the giant galaxies, we sometimes call them intermediate mass black holes, although that, you know, it's a bit arbitrary. Okay, anyway, so here is the basic Bible curve on black holes. There's a scaling relation between the mass of the black hole and the dynamics, the velocity of the stars in the galaxy, which is a measure of the mass of the galaxy, mass of the dark matter in all the dark matter. Okay, and so this is a well-known scale. It goes all the way up to the most massive black holes, nearly 10 billion solar masses, and this is the well-studied regime. And now we're beginning to collect more and more data, which suggests that there are black holes in these rather small galaxies. Now, these are seen by X-rays, okay, in deep X-ray surveys. And because you're just catching the black holes when they're shining in X-rays, it means they have a certain duty cycle, so there are far more than you see. So we're seeing of order 1% in the deep surveys, okay? That means at least 10% of these dwarfs must have black holes, maybe more. Okay, so they could be much more frequent than we might believe. Okay. Okay, and then the theorists have had a go at this too. So here's a series of simulations by Rushkov and Maddow. And what they did was say, let's assemble our galaxy out of lots of dwarf galaxies, the standard way, but let's stick a black hole in each dwarf galaxy with the usual scaling relation, 10⁻⁴ of the total mass. So these dwarfs all come together in their early gas-rich phase, and they merge together, and and they make the central big black hole. Now, the process of merging black holes is highly inefficient. And so a good rule of thumb, even without doing a simulation, is that should be as much mass in the small ones as ends up in the big one in the center, just logically. So there should be lots of 1,000 and 10,000 solar masses plus black holes out here. Most of them are naked. Some still have remnants of their dwarf galaxy around, depending on what their trajectory was. Okay, so simulations favor lots of these too. Okay, so why is this so interesting? Okay, so basically, as I said, there are these big problems with dwarf galaxies. If you're going to take the view that it's motivation for particle physics, you'd better study the astrophysics. Now, as I said, the particle physics is tailored to explain one problem at a time and can't explain them all. What do I mean by all? Well, here are 4 problems, okay, for the dwarf galaxies. And I challenge anyone to find a particle that explains all of these, for example. Not only the numbers and the cores versus the cusps, here's another one. We seem to need seeds for black holes at very high redshift, the supermassive ones. Okay, and then I'll explain this, the too big to fail problem, and finally the problem of we're finding a whole new population of ultrafaint galaxies, which are very hard to explain. So there are more reasons too. I'm not going to go into these, but let me just show you the first few. I showed you one already, but let's now talk about the cores and cusps and the numbers. Let me explain the seed problem, which is fascinating, okay? So we're measuring enormously massive black holes, okay? Redshifts 5 or thereabouts. If they grow by accretion, which is the standard route, then that takes a certain time, and there's something called the e-folding time for growth is called the Salpeter time or Eddington time, and that's about 50 million years, and there's a finite number, and you have to fold that in with the inefficiency of growth, but there's a finite age of the universe. So it turns out that if you want to grow these things, then depending on what fraction of this optimal accretion rate you have, you need seeds, these redshifts of order 10 to the 4th or 1,000 solar masses. So that's the argument. It's very, very hard to make the big ones if you start from stellar masses, from 30 solar masses or 20, more typically 10 solar mass black holes. You have a very hard time. Okay, and then this is the famous so-called too big to fail problem, I guess taken from the banking community, but it's we gave them inflation, they gave us this. Okay, so right, so one predicts lots of, in the simulations now, lots of dwarf galaxies, and these are massive dwarf galaxies. The small ones I've talked about so far are down here somewhere in terms of equivalent mass. This is the circular velocity, and so all of these basically are probably too small to be really visible. You can hide them easily, especially with known types of feedback, but you find a significant population here which are too massive to destroy by known types of feedback. Okay, so that's been called the too big to fail problem. How do you get rid of them? It's controversial. Some people in some of there are several groups around the world doing simulations. Some will say they can do this, others will say they can't. It's a debated topic. All I want to say is that if you had a black hole, that would make all the difference. That would give you immense freedom to do this. And then my final example are what are called ultra-faint, ultra-diffuse galaxies. And so these a new discovered population of incredibly low surface brightness objects, dwarf galaxies for the most part, not in necessarily very dense environments. And it's very hard to understand, I mean, how these things ended up so faint and diffuse in stars unless there was some feedback, and it's been argued that supernova feedback can't do it. Why not? Okay, so simulations show this, that if you turn on supernovae in dwarf galaxies, this shows you how much you've stripped of the galaxy, and all this stuff is gas that's fallen back in. And this is the virial radius of the galaxy. So basically, you cannot, supernovae are inefficient. The reason is that in a realistic interstellar medium, it's clumpy, and your explosions just drive out gas, but the clumps may fall back in. It's filamentary structure, all sorts of crazy things happen in the simulations, and probably in the real world. So it's very, very hard to clean out galaxies. And my only argument really is that black holes give you the new degree of freedom that might help you do this. And so why invent exotic dark matter, which can't even solve all of the dwarf galaxy problems? It just takes them selectively, one by one, when if you add in black holes, that could at least give you a new degree of freedom. And finally, it's not as though this is strange physics. It's totally accepted in the literature that when I go to massive galaxies, or I may have supernovae at the low mass end, but at the big end it's massive black holes. Okay, right, so I realize time is going on, so, and the reason primordial black holes may play a role is in the dwarf galaxies, the big galaxies get ejected. The big black holes get ejected because when I have a merger together, if I have a merger, then the logical thing is the merged black hole will get some kick from the merger in a shallow potential well. So this is an argument that if any of these arguments make any sense. Okay, so let me tell you now what else we should be doing. Okay, so dark energy, there's no definitive prediction. For the B mode polarization, there's no lower bound. The one argument that maybe does give you some hope for the future is non-gaussianity from inflation. This is looking at the second order term. Okay, and where do you do that? So the place to do that is in the dark ages. And so this is a pristine environment in between last scattering and us, where you can look at the hydrogen, okay, and study the hydrogen, the distribution of that before the stars form to mess it up. And why is that so powerful? Well, this is the history of the hydrogen temperature. Today, all sorts of complicated things heat up the temperature, but if I can study this in 21 centimeters, hyperfine structure, spin flip at 21 centimeters, great way to see hydrogen. I look at the spin temperature, the extension of this level, and I can see it in absorption against the microwave background. So it's a great way to study the universe before structure formed. And why is it so interesting for what I want to tell you about? Well, it's the ultimate flow of inflation, because here is the reason. What you're looking for is a tiny signal, okay? 10 for FNL is the current limit. Multi-field predictions, many models of inflation give you of order 1. Ideally, you want to get to 0.03 or 0.01, which is the Maldacena prediction from the quadratic corrections of vanilla inflation. And the question then is, can we improve on Planck precision by 10 or more? And I'd like to show you in my final slides that this is something we can do. And the reason is that in the microwave background, basically you have 1 million modes. So the ultimate limit with 1,000 moments, 1,000 harmonics is of order L squared. Okay, it's 1 million, and you can only get, and also you're in 2 dimensions of surface, so the ultimate accuracy is 1/n, 0.1%. You can never do better with anything in the microwave background. Stage 3, stage 4, stage 5, whatever you want to do, okay, you're limited there. So how do we increase that? Well, you go to galaxy surveys. A whole new industry is beginning in our field, okay? Billion galaxy surveys. Maybe you can get 1 billion galaxies, but galaxies are highly dangerous probes, and the best bias, and the best you can already do is 10 to the 8th. That's 100 times better than the CMB, 10 times better in accuracy. So suddenly we can do 10 times better, but there's one more way to go, okay, which is the ultimate way, and that is going to the dark ages. And in principle, by going to the building blocks of galaxies, you suddenly can get the equivalent of vast numbers of equivalent clouds. You won't see them directly, and also you have 3 dimensions to work in, and that can give you 10 billion modes. Okay, so the way this might work, another way to think is the following. This is what we have on the CMB. Okay, this is where we're stuck with our 1 million modes. If I can go to the first clouds, this is the power spectrum for the first clouds, and this is where all the extra modes come in. I can now go from, in the inverse wave number space, from k's of order 0.1 up to k's of order 10, and so that's, that's about 1,000 in scale, or 10 to the 9th in mass from massive galaxies. and so I can suddenly have a hope of beating down my limit, which was 1 over root n to the minus 3 for the combination of F and L and the temperature perturbations, by opening up to many more modes, and in principle beat it down. So how many modes can I get? Sorry, and so this is another way to look at it. This is a prediction made of the increase, and this is now the spin temperature you're looking for of tens of milli-K, absorption against the CMB, and this shows you that you have to go from the CMB, typical constraints, arc-minute scales, down to arc-second scales, and you have to go to very high redshift, actually, to pick up this significant factor. This is the redshift range, 40 to 80, maybe 50, so 50, maybe 30, to get significant things, and going to these very small angular scales. Okay, so that's the problem, and you read 10 to the 12th modes, a few arc-second resolution, and the beauty of this is that you can slice the sky up by doing tomography, because it's a three-dimensional study, okay? So you don't actually need to get 10 to the 12th modes on the surface of the sky. You can get by with 10 billion and slice up in frequency by 100, okay? Okay, so in principle you can gain your 1,000 over the CMB, in principle, okay? Okay, so why is it so hard? Well, the reason you can't do this easily from the Earth is that everywhere you are, even in Western Australia where the SKA is being built, there's all this interference at low frequencies from everything, from mobile phones, from internet, whatever. In addition, you have the ionosphere. And the only place to go to do this properly is the far side of the moon, which is the most radio-quiet environment in a solar system. Okay, so 21 centimeter astronomy in the dark ages. That's what we want to do. Okay, so here is what you need, okay? The optimal bandwidth should be slicing up by a megaparsec or so. That means 0.1 megahertz. You want to do this maybe at 30 megahertz because you're trying to get to redshift of 50, for example. You want to resolve a few arc seconds. That's 100 times better than the CMB can ever do, to L of 10 to the 5th, at a wavelength of 10 meters, okay? That's redshifted 21 centimeter by a factor of 50, okay? And you're looking for a 10 milli-K signal against the foreground, which is 1,000 Kelvin. So it seems that's from the galaxy. It seems totally hopeless, okay? But, one can put in some numbers. I should say that LOFAR can beat down foregrounds by 10 to the 5th. That is not a real problem because the frequency structure, etc., is so different from what you're looking for. So the optimal array size might be 100 kilometers. That's just based on the wavelength and the number of modes you want to go to. For 10 meter, you need millions of dipoles because you need to basically cover your area. Okay, that's the ratio of the diameter to the number of the area of your array to the area of your single dipole, of order tens of millions, and this is the number of passengers on the sky to get to your 10 to the 12th. Okay. And so you have to remove the non-Gaussian foregrounds at this level. I'm not sure that's a great problem, but it has to be shown, of course. And in principle, you can gain up to 1,000. Okay, so how does this work? Okay, so the world's best attempt to do this so far is Chime in Canada, and you can see they have 1,000 antennas. You have to correlate everyone against everyone, and they work at 400 megahertz. That involves 10 to the 15 multiplies per second. Okay. To go to my million or 100,000 antennas, you can see that would be significantly more. But to do this with 1 million antennas would mean going up to 10 to the 20 multiplies per second. You win a little with a lower frequency, and you just have to hope that in the future we'll be getting there. That's 100,000 more times more computing power than we have now, but it seems quite possible. So the far side of the moon, here's a schematic deployment for that. A study from JPL a couple of years ago. You lay down tracks with a lunar rover on the far side of the moon, and these are dipole antennas, and you have a big correlator somewhere, or possibly in orbit around the moon. Why is this so interesting now? Because there's been a whole new interest in the moon. This is the south pole of the moon, and so there are some craters here which are permanently in shadow. It's on the side of the moon as we see it, so it's always in more or less twilight. It never gets too hot or too cold, and this crater in particular is full of ice, and the edge is so high that it's in perpetual sunlight. And this is a thermal image showing how cold it is in the interior. This is a great place to do infrared astronomy. It's also a great place to set up your lunar station, which is exactly what ESA is dreaming about. And so this is the sort of thing, what they call a moon village, which is so far, the ESA Director General discusses doing business and tourism. The business actually is helium-free mining. That's a whole other story. But, you know, science is a good thing. So here is the program one can try to sell to ESA, if not the US, or to China, whatever, to do CMB, certainly on the ground and in space as well. Sorry. To do optical surveys, so we want to get up from FNLs of 10 down to a order 1 maybe, and then, but even this is debatable, but if we can actually proceed to get our million antennas on SKA, that may help a lot, but the far side of the moon eventually will get us up to maybe FNL of 0.1 and eventually maybe down to 0.01. And why this is so exciting is that, of course, there are modulations on the sky that inflation models predict that you could hope to see and actually identify the specific inflation model in principle. Okay, depending on the inflation model, which has the features in, it gave you the primordial black holes. So there's a connection with everything. So to summarize, sorry, I've gone so long, dark matter may be primordial black holes over a broad mass range, this is the mass range 1,000 to 10 to the 5th that can certainly be very important for dwarf galaxies, and forming them requires some sort of non-gaussianity, and that's also the ultimate part of inflation, and going to the moon may be our best way in the future, and I mean 2035, 2040, to really do cosmology much better than we do now. So thank you.